So what are vector valued functions good for? It's a good question. And they're good for a lot of things. But one of the applications, which is really powerful, is to model motion in either 2 dimensions or 3 dimensions. In fact, that's what our physics brethren use it quite often for. So we're going to look at that. And some of these concepts you may have already seen in a Calculus 1 class, which is good. So they kind of translate over here to Calculus 3, which is wonderful. So let's take a look. We're going to look at velocity and acceleration, and we're going to look at projectile motion today. So as an object moves along a curve in the plane, what does plane mean? Does that mean a jet plane? What does it mean?
2D.
2D, very good. So let's look at 2D motion first. The coordinates x and y of its center of mass are each functions of time t. And we could use f and g to represent the 2 functions, but right now I'd like to just sort of switch notation. We'll have x of t and y of t. It's the same thing though. So our position vector, r of t, looks like this vector. So if you have this vector, which represents the position anywhere in 2 dimensions, and you can always find that position by looking at the tip of that vector, and then remember we graph it by connecting all the tips. Here are the definitions for velocity, acceleration, and speed. Velocity is itself a vector. It's simply the first derivative of the position vector. And you probably saw this in Calc 1. Did you not, when you had to do some sort of motion kind of problems? It was like, oh yeah, the first derivative is velocity. And the second derivative is acceleration. Now here's something different that you did not learn in Calculus 1. I guarantee it. Because they don't have enough information, and this is why vector valued functions are superior to how you studied motion in Calc 1. These are better because it gives you more information because you have a third variable in there, time t, to tell you at what time the object is at a position. So speed, which a lot of times students confuse and they think that speed and velocity are the same thing, they are not. Velocity is a vector that has magnitude and direction, and speed is simply the magnitude of your velocity. So speed is a scalar, not a vector. And typically it's a scalar function because it's going to be a function of time t. Now let's look about motion in space. What does the word space mean in this class?
3D.
3D. So similar definitions here. So if you have a position vector right there, x of t, y of t, z of t are the components, your velocity is still going to be a vector, and it's the first derivative, only now you have a third component. Acceleration is still the second derivative. And speed, which is still going to be the magnitude of your velocity vector, which is the same as the magnitude of the first derivative of your position vector, and that can be found by
Integrating the velocity, or
speed. We're working on speed right now. Speed is a magnitude. Yeah? So fill in the blank, and then we'll move on. Let's look at motion of a particle in 2D. And here we can use your graphing calculator to graph this in case you're wondering. So you can easily go to, and I have your calculator ready to queue up here. Where is it? Ooh, not that one there, right here. So if I go into mode, and we're in parametric mode already, which is good. So that you want to make sure you're there. And let me also check, I'm in radians mode also because this function is going to be a trig one. So I go to y equals, and then I'm going to have 2, let me do a clear, 2 sine of t over 2. Okay, t divided by 2. And then if I go to my y component, let me clear this out, I have 2 cosine t over 2. And then I'm going to check my window, and let's see, my window is -10 to 10, which is plenty. That's fine. It's actually be a bit much because it's going to wrap around itself. So I'm going to cut back on the range here. I'll have my t minimum be 0. And just for kicks and giggles, I want you to see what would happen if I put my my t maximum as being just pi, and then I hit graph. You'll notice I get just a portion of the graph, and it looks like it's kind of curvy there, but if I go to my window here, let me change the maximum to 2 pi to see what happens here. Hit graph. Ooh, wait a minute. Interesting. And maybe I could get more of the picture if I go to window. And maybe I need to have my T max be, I don't know, let's see what 4 pi gives me. Okay. Hit it. Oh, there, it gave me a full circle. Nice. And it looks like it's a circle centered at the origin of radius what?
Is that
0,
2?
0?
Yeah, the radius is, it looks like it's going to be 2. And in fact, it is exactly that. So what was the orientation, though? Did it look like it was a clockwise or a counterclockwise circle?
It's actually clockwise.
It was indeed clockwise, if you noticed here. So if I had to eliminate the parameter, I would probably need to solve for sine, solve for cos, because you'd want to use the cos squared theta plus sine squared theta equals 1 business. I'm not going to do that here, but I'm just going to say you better know how to do that. Okay, so there's the graph. Now, what about velocity and acceleration? Okay, well, velocity is a vector, and you can just get it easily by taking the derivative of the components of this position vector. So using a chain rule, I'm going to have 2 times a half times cos t over 2. And of course, I can reduce. Those 2's will cancel. And when I take the derivative of the second component, derivative of cos is negative sine. So I'm going to have negative 2 a half sine of t over 2. And of course, these 2's will cancel. So you can reduce to lowest terms. Your acceleration vector can be found by just taking the derivative of velocity vector. So here I'm going to have negative a half sine t over 2 for the first component of acceleration, and then for the derivative of the second component, let's see, I'll have negative a half cos t over 2. Okay, and I'm done with finding velocity and acceleration. Now, what about speed? They didn't ask me yet, but in part C, they are. So how do you get speed?
It's the magnitude of the velocity vector.
Exactly. So you're going to go, okay, I'm going to just take the square root of the sum of the squares. But then, wait a minute, what happens, when you square a negative? Isn't it really a positive? So don't you get cos squared a t over 2 plus sine squared t over 2? What does that end up being after you use a trigonometric identity?
1.
Does that always happen with speed? No, 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 no. Most often you're going to get a scalar function for speed that's some function of time t. This happens to be a constant, though, which is kind of cool. Now, what happens when your speed is constant? What does that mean? And we'll look to see some more about this later. But what happens if you did take a velocity and acceleration's dot product? What would you get?
There's no acceleration, 0, right?
Well, no, the acceleration is not 0. Certainly, acceleration is this vector right here.
Oh, whoopsie.
It's
They're
a
orthogonal.
lovely vector. Yes?
The dot product is orthogonal, so it equals 0.
Yeah, if you take the dot product between these two vectors, and you guys know how to do that, so you'd have like cos t over 2 times negative a half sine t over 2 plus, and then I'd have a negative sine t over 2. That's the component of the second component for velocity, and then multiply that by negative a half cos t over 2, like so. What happens? Well, if I do some cleaning up here, I hope you notice that this negative a half will go in front. And then here I have a negative times a negative, but that's a positive. And aren't these like terms, folks? What happens when you add up these two terms?
0.
You get 0. So what does that mean for this problem, not all problems? Like, don't be thinking, oh, this is a pattern. Every single vector valued function has this happen for it. No, 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 no. For this problem, this circular motion, it turns out that velocity and acceleration are orthogonal to each other. because their dot product is 0. That's cool. That's really cool. Let's do another example. This example is pretty hardcore. And a couple years ago, I had a student who wanted some tutoring on this problem after the fact. Like, he had me for Calc 3 like 2 years before that, and I guess he forgot all his Calc 3 with me, and he was taking a physics course, and he was like, oh, how do I do this problem? I go, dude, did we not do that in lecture? And we went over it, and he goes, oh yeah. So this is going to help your physics. So if you're going to take physics, you may want to pay attention here. So first up, I'm going to graph it using my graphing calculator. Let me get back to that. So the first component is t squared minus 4. And it looks like my second component is just simply t. That's easy. And let me just check my window. I have currently the window going 0 to 4 pi. If I hit graph, the problem is it's only going to give me half of the picture, which is, I'm going to have to mark you wrong. So what is the full picture? Well, if you go back to window and capture some negative time, like -10, and I'll leave my t max 12 and some change, you'll notice, there we go. There's the full picture. So it looks like a horizontal parabola. And did you notice the orientation if you didn't blink too quickly? So here's my parabola. Was it going, was it going this way or was it going the other way? And yes, it matters, because if you don't put an arrow on your graph to indicate the orientation, I can't give you full credit. Anybody know?
It was upwards.
Yeah, it was this way. Okay, so now how do you find velocity and acceleration vectors at t equals 0 and also at t equals 2, and then actually sketch those vectors at the appropriate positions at those points? So the first thing I'm going to do before I find velocity and before I find acceleration is what is the position at these 2 points? I get that the time is 0 or the time is 2 seconds, but what's the position? You use the position function that they gave you. So that will give you the coordinates of your position. So if you substitute time t equals 0 seconds into your position function, you'll find the point -4, 0. So it's right there. This is where the object is located at time t equals 0. At time t equals 2 seconds, I'm going to get the position 0, 2, right there, when time t equals 2 seconds. Okay, so that's the first thing that you should probably do before you start moving forward in this problem. So now let's go ahead and get the velocity vector and the acceleration vector. Fine. So r prime, there's our velocity vector, super easy, it's just 2t1. And acceleration is just the derivative of velocity, so that's just going to be a constant vector, 2, 0. Does that always happen? No. Sometimes your velocity vector is a vector valued function that has some time t in there. This happens to be just pure scalars for components, and that's known as a constant vector. Fine. Now, at time t equals 0, what do our velocity and acceleration vectors look like? And let's graph them. So the velocity vector, when I substitute in time t equals 0, I get 0, 1. And the acceleration vector, when you substitute any value, because it's a constant vector, it's always going to be 2, 0 regardless. So now let's graph those, but we're going to graph them at the point when t equals 0. So they're going to sprout out of this point. Now normally we graph vectors in standard position. In other words, where their initial point is coming out of the point 0, 0, the origin. But when you do one of these problems, you don't do that, okay? So watch closely how I'm going to roll. The first thing I'm going to do is I am going to graph these in standard position. So the vector 0, 1 can be graphed by first graphing the point 0, 1, that's its little tip, and then graphing in standard position. So there's the velocity vector. You're going to translate this vector, in other words, move it, because it just represents every single vector in the universe that has that magnitude in that direction. And you're going to move it so that it is, the initial point comes out of the point that it's associated with it. So there is r prime of 0. Now let's do the acceleration vector. Well, the acceleration vector, if you graph that guy in standard position, you first find the point 2, 0 right there on the x-axis, and then you graph starting with the initial point at 0, 0. And then you translate this guy. Notice he's 2 units in length. So there's your r double prime of 0. So notice that in this particular case, the velocity and acceleration vectors do look like they're orthogonal at that moment. Now let's do some analysis for time t equals 2 seconds. Over here I'll do at time t equals 2. What are the velocity and acceleration vectors doing then? R prime of 2 is going to be 2 times 2, 1. So that's going to give me the vector 4, 1. And acceleration is still going to be this constant vector 2, 0. Nothing's changed. Sorry, I'm having some Surface Pro problems. Okay, so now if I graph these guys in standard position, if you find the point 4, 1, oops, that's not to scale, 4, 4, 1, it's right about there. There's the point 4, 1. And then graph a vector up to that point. There's your velocity vector, and you're going to translate this, but you're going to have it sprouting out of the point that it's associated with. So this vector here has to come out of this point here. So you're going to go 1, 2, 3, 4, 1. It's going to be roughly right around there. So that vector, I got to maintain its integrity. So I have to keep it pointing in the same direction and have it exactly the same magnitude. So that vector right there is r prime at 2. And what about the velocity, or excuse me, the acceleration vector? Well, the acceleration vector, as we discussed, is always this constant vector 2, 0. So coming up here, he's still going to look like this horizontal vector. That green one there is r double prime of 2. Now, what I want you to notice, and I'm done with this problem, but here's the key point. Look at the velocity, and by the way, these vectors here, the velocity and acceleration, they're definitely not orthogonal over here at time t equals 2 seconds. Can you see that? They're not orthogonal there. But I want you to notice the acceleration vector. Do you notice how, excuse me, the velocity vector? Please note the velocity, and this is answering this last question. What do you notice about the velocity vectors in their relationship to the line of motion? And you better get this key point. Velocity vectors are always tangent to the line of motion. Velocity vectors are always tangent to the line of motion. That is a key fact, people. Please never lose sight of that fact until the final exam. So keeping that in mind, I'm going to do example 11 right now, and then we'll take a pause for any questions on these two examples here. So example 11, we're going to start an object. Oh, I see what I'm doing here. Hang on a second. This is the wrong. Is this what you guys have in your course reader by any chance?
Yeah, that's what we have.
Use example 11.
Yeah, you have example 11 like this.
Example 11 is, or example 12 is example 11 for me.
Right, right. I think you have these switched, and I think I've got the wrong PDF here from, because I changed things over the summer, which is kind of interesting. So what
I think it's our example 13.
Yeah,
Yeah.
example
Example
13 is example 11.
Yeah, example 11 is really, yeah, you got, these are out of order, in other words, right?
Yeah.
Hello? Okay,
Yes.
let me just look at something real quick. See here, I gotta, hold on a minute, let me go over here. I thought I updated my little flash drive here, but maybe I forgot to put it over here. Sometimes my computer does not give me the whole business. Let's see here. Let me just see if I have this one being the one that, very strange. Okay, we're getting close. Let's see if this is, yeah, this is not the one. Okay, hang on a second. What I'm going to do here is I'm going to crash out and save this. That's a bummer. And then I'm going to kill off this flash drive. You live in Spain, but the S is silent. Hilarious. Yeah, this class is going to be some pain for you. Sorry, dudes. That's how it is. I don't know why this is not getting killed off. Let's see. Let's do file. It's not wanting to go away. Okay, let's do. Okay, so I'm going to hopefully get, sorry about the delay here. Hold on a quick second here. I'm going to check something. Let me put this on pause while I'm. So the fact that velocity vectors are tangent to your curve is going to show up in this example. So it's really important that you get that. This is key. So they want us to find a set of parametric equations for a line that's tangent to this space curve. This is your position vector right here at this point. Now this problem is a little bit tricky. So if you don't understand the concept of vector valued functions, or you just have a very surface knowledge of it, this problem is not going to go well for you. But before I even do it, I want to remind you that this is basically a Calc 1 problem in 3D. So let's do a quick review of what this problem has to do with that's similar to Calc 1. In Calc 1, please remember that one of the things that you probably did multiple times is you were given some graph of some function, say y equals f of x, okay, and then they maybe picked out some point down here, and they said, hey guys, could you give us the equation for the tangent line at the point when x is equal to, you know, something? Let's say here was, I'll just put 2 or something. At the point when x is equal to 2, did you remember having to come up with equations of tangent lines in Calc 1? Please say yes.
Oh, yeah.
Yes, definitely.
Thank you. Okay, wonderful. You're going to do that right here in 3D. That's all we're doing now. Except remember, in 3D, you're going to have a space curve, which is given by a vector valued function. So you're going to have some weird R of t here. And they're giving you, you know, some point 0, 4, pi fourths or whatever have you. Like, let's just say the point P is right there. And then they're going, well, hey, guys, if I draw a tangent line to that point, woo, give me the parametric equations. Because remember, in 3D, you don't have a single equation that represents a line. You need a set of parametric equations. And so that's what they're doing right now. So how do you do that? Very carefully. The first thing you're going to do is remember some knowledge from finding parametric equations for a line. One of the things that you remember is you need 2 pieces of info. You need a point that lives on the line, and good news, this point right here, P, is going to be a point on that tangent line. And what other piece of info do you need? I'll open it up to see if anybody remembers.
The derivative of the tangent line. Not
I'm not talking about derivatives here at all. I want to know what are the
The direction vector.
Thank you. Yes, thank you, Rosie. That is correctamundo. You need a direction vector for your line. You need a direction vector for your line, and I don't have one. They didn't give me one. And you better not use this vector, because that vector is a position vector. That's not going to give you the direction vector for your line. So it turns out to get this direction vector, you're going to go get r prime, because we know that velocity vectors are always tangent to the line of motion, but that's not going to be enough, because that's going to give me a collection of vectors. This thing is going to be, you know, giving me all kinds of tangent vectors, depending on where I am on the curve, and the curve is changing, varying all the way around. So that direction, the tangents are going to be all over the map. But you'll have to evaluate it at some time that is the same time t that this point is. And so what we haven't done, and we will do right now, is at the point, in this case 0, 4 pi fourths, what time is it? So what time, and we'll go get the velocity vector in a moment. What time t is it at the point p 0, 4 pi fourths? And don't guess. Don't go, oh, I don't know, t equals 57. You don't know. So what you're going to do is, since this is a position, you want to compare these two, the components of your position function with the coordinates of your point. So what you need is 3 cos t has to be equal to 0 at the same time that 4 sine t is equal to 4, at the same time that 1/2 t is equal to pi fourths. That better be the same time t for all of those guys. So can you guys notice that, and you can even do this by inspection, what time t do you think it is to make all of these equations true at that same value of time? And one way is pick which one looks easiest to solve for time t, and then double check it that it makes the other two equations happy. Pi what?
Over 2.
Yeah, if I multiply
Pi
both
halves.
sides by 2 here, I'll get pi halves. Now, does that, double check it, if you plug t equals pi halves into the other two equations, does it make those equations true? Yes or no?
Yes.
Yes, it does. So this is the correct time at this point t. So time t is equal to pi halves seconds. Okay, fine. Now what? Let's go get the velocity vector, and then we'll evaluate a velocity vector at time t equals pi halves, and that will give us the direction vector for the line, the tangent line. So r prime is, and now you guys know how to take derivatives of vector valued functions, I hope, because you did that on your quiz. So let's see, the derivative of 3 cos minus 3 sine. And then the second component, the derivative of 4 sine, I believe is 4 cos. And the derivative of 1/2 t is going to be 1/2. And then the actual direction vector will be r prime evaluated at time t equals what?
Pi halves.
2.
Pi halves. And be careful that if you don't find an actual constant vector for your velocity vector, like I get students who actually use this guy right here, the velocity vector, which is a function of time t, and they use that and plug it into their parametric equations, and I just take away all their points. I'm like, what are you doing? Your direction vector has to be a constant vector. It has to have like pure numbers only as components. You don't have like, functions of t when you're finding the direction vector for a nice straight line in 3D. So then, using your knowledge of trig, let's see, sine of pi halves, I believe, is 1. So this is going to be minus 3. Cos of pi halves is 0, so I'll have 0.5. Okay, great. So this is the direction vector for my line, and I already have a point on the line. So I'm ready to just go ahead and do my parametric equations. Boom, boom, boom. I'm going to use the coordinates, 0, 4 pi fourths. That's from the point P up here. That's the coordinates, plus or minus, the coefficients of my time parameter t here are here, plus 0, plus 1/2 t. Now, folks, really, I don't want you putting the plus 0. So ideally, once you, put everything in the right slot, you can safely get rid of the plus zeros or the zeros and so on. So your final answer for this problem, the parametric equations for a line tangent to your curve, is that guy right there. Okay, questions?
Pretty straightforward.
It is. Okay, now let's do something that's also pretty straightforward. Let's say that somebody gives you a position function. Okay, there he is. And hey, just go get velocity, speed, and acceleration. Well, you're just going to use the definitions that we did at the beginning of lecture. No problem. Velocity, that's just the first derivative. So you're going to go, oh, easy peasy, 3 cos, minus 5 sine, and 4 cos. Okay? And then acceleration is the second derivative of position. So I get minus 3 sine, minus 5 cos, and minus 4 sine. And then speed, remember, is the magnitude of velocity. So you got to be careful here. You're going to be doing a magnitude of a vector. So you're going to have the square root of the sum of the squares. And I know that there's a negative 5 sine there, but I'm going to purposely ignore the negative because I know that whenever I square a negative, well, you know. Am I done?
The like terms.
Yeah, you want to combine like terms here because you can't. So always try to see if you can't clean something up all the way. I'm noticing that I have a couple of cos squared terms here, and you can combine those, and then voila, I think I can use one of those lovely trigonometric identities, right? What is this going to be equal to? Square root of what? You see if I factor out
1.
25 from this radical, you're
26.
gonna, careful whoever said 26. This is 25
Sorry, 25.
times 1, but
Yeah,
that's
20.
going to be square root of 25, which is a 5. Yes? So speed is a 5. Fine. Now let's do a tough problem that involves some knowledge from the last section. And I love these kind of problems. Hint, hint. You'll probably see one on the midterm. So an object starts from rest at this point, 1, 2, 0. And it moves with an acceleration of, and they're giving you the acceleration vector there, but they're giving it to you in the format with the linear combo of the standard unit vectors. And acceleration is going to be measured in feet per second, which is also known as feet per second squared. Find the location of the object at time t equals 2 seconds. This is a multi-step problem. You're not going to get it in 20 seconds. You're going to have to work it. So the strategy is they gave me acceleration. And in fact, you know, they gave me some initial values here too. So I'm going to go get velocity, which means I'm going to have to integrate acceleration. And then I'm going to have plus a constant vector. So then I'm going to have to use my initial velocity to get the overall velocity vector. And then I'll integrate again, because integrating velocity gives me position, and then I'll again have a plus a constant of integration, and then I'll use the initial position to get that constant vector satisfied. And then finally, at the very end of all that, I'll plug in time t equals 2 seconds. Okay, so let's start. So velocity is equal to the integral of acceleration with respect to time. So I'm going to rewrite acceleration as a vector in component form just because it's easier. And then knowing that I'm just going to integrate each of those components separately, I'm going to get a vector. What is the integral of 0, people?
C.
It's 0 plus
C.
a little bit extra. C what? I want a subscript.
C1.
C1.
C1, thank you so much. And yes, it matters now. If you just do plus C, like out here, I'll dock you points because that's not going to give you enough subtlety or nuance for you to get the individualized constants of integration. And this is one of those problems where you're going to have to. It's like a particular solution problem on steroids. So then what is the integral of 1?
T plus C2.
T plus C2.
Yep. And then how about the integral of 2?
2t plus C3.
So now how am I going to get C1, C2, and C3? Do I just guess? No, you use initial condition. But they didn't give me one. But it's disguised. And this is where our physics folks try to trick you. But you got to think. Since the object starts from rest, what does from rest mean? It means that your initial velocity is the 0 vector. That is, velocity evaluated at 0 is 0, 0, 0. So knowing this, and knowing that this right here is our velocity vector so far, I hope you can see that if you evaluate our velocity vector at time t equals 0 and substitute zeros in place of the t's, you'll get that C1 and C2 and C3 all happen to be 0. Will this always happen? No. I always give you much harder problems where your C's aren't always 0. That's because I like to see if you're really paying attention. So what do we have so far? We have that velocity is this vector here, 0, t, 2t. Great. Now what? Well, now you can go get position. So position is going to be found, we'll call it r of t. That's classic. You're going to integrate your velocity vector with respect to t. So you're going to integrate this vector 0t, 2t. And you're going to use the same type of formatting with your constants of integration, but I'll use double subscript. So the first component, the integral of 0, is 0 plus C11. The second component's integral is t squared over 2 plus C22. The third component is the integral of 2t, which is simply t squared plus C33. Now what? We need to get the C11, the C22, and the C33. How? Well, you use initial condition. They told you that the initial position, this means at time t equals 0, is 1, 2, 0. So they gave you enough information to figure it out. So the initial position, this is one of the initial conditions, they told us essentially that r of 0 will give me, sorry, my computer is really slow right now. 1, 2, 0. So if you plug in, if you go r of 0 right here, you'll get 0 plus C11, 0 squared over 2 plus C22, 0 squared plus C33, has to equal 1, 2, 0. And so you equate each of these components with each other, because you know when one vector is equal to another, you can easily see that C11 will end up being 1, and C22 will be a 2, or excuse me, yeah. And then C33, this is going to be easy, will be a 0. So what do we have so far? We're almost done with the problem, but not yet. So far, our r of t, our position function, that's a vector value function, is going to look like 1, comma, t squared over 2 plus 2, comma, t squared. Now we can answer the final problem. They want to know what's the location, the position of this object at time t equals 2 seconds. No problem, we have enough information now. We're just going to evaluate our position function at time t equals 2 seconds. So that's just substituting. And we'll get this position, 144. And that's the final answer to this problem. So I told you it was going to be a multi-step problem, and there you go. Woo! Had to integrate twice and have fun and all that good stuff. Okay, so now I'm going to put you in breakout rooms and have you give it a shot. So you and a buddy are going to try your hand at example 14. What do you think, huh?
Oh, so you know what I was muted this whole time? Yes.
Okay, so I'm just going to throw you in your rooms. Enjoy. I may come in there and check up on you. Bye. Okay, and so you're saying that minus cos 0 plus C1, that's a C1, comma, 0 squared over 2 plus C2, comma, 2 times 0 squared plus C3 is going to be equal to 20. And so you're going to equate these. So 20 had better equal minus cos 0 plus C1. 0 is equal to 0 squared over 2 plus C2. And 0 is equal to 2 times 0 squared plus C3. David, can you see what I'm doing?
Yes. The 1 from the cosine is added to the 20. Right.
Yeah. So you see here that when you add 1 to both sides, you will get a 21 for C1.
Okay.
And then here it looks like you're going to get C2 is 0. And here it looks like C3 is 0 also. So your velocity vector had better look like this. Minus cos plus 21 t squared over 2, 2t squared, right? And then you'll integrate that to get your position vector, okay? And then use this as your initial position, which is time t equals 0. The position is 0, 0, 1. So I think that Nick did okay. So Nick, congratulations. You got the right answer. That is awesome. Okay. Woohoo! All right. How about differential equations?
Yippee.
Yeah, this isn't really a differential equation problem that you'll see in a DiffyQ class, so it's okay. All right. I know some of you may have had some negative experiences about all they're saying is dr dt is equal to that vector. So remember, a differential equation is just an equation that has a derivative in it. So that's a derivative, but isn't that velocity? Hello?
Yes.
Say yes. So if you want the position vector, you're just going to go, well, that's r of t. I'm just going to take the integral of dr dt with respect to t. So I'm just going to integrate t cubed plus 4t e to the negative t 2t squared with respect to t, and I'm going to do this fairly quickly because I want to get to projectile motion. So I'm going to end up with a vector, and I'm going to, let's see, t to the 4th over 4 plus 2t squared plus some constant of integration, and then the antiderivative of e to the negative t is negative e to the negative t, and I'm going to add a constant of integration of that guy, and then 2t squared has an antiderivative 2/3 t cubed plus some other C3 constant of integration. Now, they did tell me that the initial condition, r of 0, I'll put it in component form, is I plus j, but that's 1, 1, 0. Remember, we're in 3D, so you want to use the 3 components. So if I, everywhere I see a t in this vector, I plug in zeros, I'll have 0 to the 4th over 4 plus 2 0 squared plus c1, negative e to the 0 plus c2, and essentially 2/3 0 cubed plus c3. So when I equate these, so 1 is equal to 0 plus c1, it looks like I will have, sorry, it looks like c1 is going to be in fact just the 1. But then when I equate the middle components, I got to be careful here because e to the 0 is not 0, right? If I add 1 to both sides, it looks like I'm going to get c2 is equal to 2. And then here, when I equate the components, the last components, it looks like I will have that c3 is in fact equal to 0. So the final result is the position vector is going to be t to the 4th over 4 plus 2t squared plus 1. And then the middle component will be negative e to the negative t plus 2. And then the last component will simply be 2/3 t cubed. And there's your final result for that guy. So we're officially done with that portion of section 14.3. And now we're going to do the hard part, projectile motion. So some of you have seen this in physics. If not, you will see it in physics. So let me address this issue right now, because I've seen this problem already. For those of you who have some handy physics formulas for certain things, I will not accept those physics approaches or physics strategies to find the answers on my quizzes or exams. Okay, now homework is fine because I don't really check your work when you're doing homework. So, you know, if you want to go do it your way, and I know some of you think that, hey, your way or the highway, and you're not open to learning the approaches here in Calc 3, I'm just going to tell you right now, prepare to die. Because I've seen when I give these lectures here with projectile motion, we're going to use our vector valued function knowledge here in order to do this problem. And then when I see students who don't want to learn anything new, they already know how to do this from physics, you know, mg sine theta or whatever your formula is, and you do it that way, and you even if you get perfect answer of all the points my math lab, I'm just going to proceed to zero you out, 0, 0. Because I want to see it done this way. And this way is not hard. This way, I'm not just going to hand you a set of formulas and go, oh, go to it. That's not how we do it here. What we do here is a gut level understanding of what's going on and not just a bunch of party tricks using formulas. So I'm just giving you a fair warning right now. For those of you who are like, well, I'm going to fall asleep right now. I already know how to do this from physics. Maybe not. Math is the queen of all the sciences. So physics got this from math. Okay, so first up, the picture of the projectile motion essentially that we're going to look at, this is a generic look, but it's going to be traditionally like an upside down parabola. So some object is going to get hurled, like a baseball or a football or something gets hurled up, and the only force acting on it after it gets hurled is due to gravity. So it's going to go up and then it's going to come down and smash on the ground. Boom, and we're done. So let's take a look at the force that's acting on this object after it gets released. So the force due to gravity is downward because gravity pulls us down, and you can't have scorn for the laws of physics. So your force vector is negative mg j hat, which if I write this in component form looks like this, 0, negative mg, same thing. And the acceleration due to gravity depends on if you're using the metric system or the English system. So you have to be careful when you're doing one of these word problems. This is going to be on the midterm. If you're given feet and other things in terms with distances being feet, or your velocity, initial velocity is feet per second, you're going to use the English system and you're going to substitute 32 in the place of the g, because that'll stand for 32 feet per second per second. If the word problem has meters or your initial velocity is meters per second, then you're going to use, I typically just round that to 9.8 myself. You'll use 9.8 meters per second squared. Okay? So know this, because I'm not going to tell you in the problem. You have to kind of have those numbers handy and ready to go depending on your problem. So by Newton's second law, the same force here that we're talking about is due to the acceleration, because that's Newton's second law. So the only physics that I remember, and this is a key formula from physics, is F equals ma. F is a vector, acceleration is a vector, m is mass, which is a scalar. Okay, now these two vectors have to be equal. So we're going to set these two vectors equal to each other. And so what happens when we set those vectors equals to each other? You're basically saying F has to equal F. So this vector 0, negative mg had better be equal to ma. How about if I do it this way? I won't do component form. I'll do negative mg j hat has to equal ma. So if I divide both sides of this equation by m, assuming m is non-zero, I get negative g j hat has to equal the acceleration vector. And this is basically your key here. So your acceleration is which is due to gravity, is negative g. G is a constant, and it's j hat. And it's negative because it's pointing down. And by the way, this is a constant vector. In other words, it never changes as long as the object is only getting operated on by gravity. So this vector, they're drawing the vector A for you here in the picture. And it's no matter where you're located, it's always pointing downward, and it's always the same magnitude, and the direction is always down. Okay, so now let's derive the position vector. And it's going to be a vector value function. I don't care what they taught you in physics. Delete it from your brain cells. You're going to do it this way. I'm going to do the whole derivation, and we already did a similar process, because when I did this example way back here, example 13, where I had to integrate twice, they gave me the acceleration vector here, and then I integrated once to get the velocity, and then I used initial velocity to get the constants. And then I integrated again to get my position vector, and then I had a new set of constants, and I used initial position. I'm going to do that all over again, but we're going to do it with some generic initial conditions, okay? So the generic initial conditions are, you have a projectile of mass m, okay? Your initial position is r naught. That is a vector, okay? So some initial position. And then you're going to have initial velocity, v naught, okay? Now let's do the derivation. So we're going to start with the acceleration vector, And we know that he looks like, if I do it in component form, it's 0, negative g, which is the same as negative g times j hat. So then velocity is the acceleration's integral. And so you're just going to go, okay, what is the integral of negative g times j hat dt? And that's going to end up being negative gt times j hat plus some constant vector. I'll call it c1. So that's a constant of integration. But how do I get c1? Well, they gave you initial velocity. V evaluated at 0 seconds, which is negative g times 0 j hat plus this constant vector, has to be equal to the initial velocity vector. Okay, fine. And that just means that your c1 is the initial velocity. Fantastic. So what do we have so far? We have that velocity is v of t, which is negative gt times j hat plus some initial velocity vector. Fine. Now what? Go get position. So the position vector, that's what we're trying to get at. That's what we're going to call it r of t. That is just going to be the integral of velocity. Okay, fine. So you're going to integrate negative gt j hat plus this vector v naught, and you're going to integrate with respect to time t. So then you go, oh man, okay, what do I get for this integral? Well, when I integrate t with respect to t, I get t squared over 2. So that first term will be negative 1/2 gt squared times j hat plus the v naught constant vector times t plus some other constant vector, we'll call it c2. But then to get c2, you're going to use the initial position, which basically states the following. R evaluated at 0, which if we do plug in 0 everywhere we see a t here, you're going to basically have, come on, baby. 0 j hat plus 0 times v naught vector plus c2. That has to equal r naught, but that just means that your c2 vector had better be exactly the same as your initial position. And now we're done. And now I'll put the grand finale right here in this theorem box. So ready? You're going to write this down. R of t is going to equal, here we go. You're going to have negative 1/2 gt squared times j hat plus t times v naught. And we're going to have to clean this up some because it's kind of too generic. Plus r naught. But then, what they gave us some other stuff. Usually what they're going to do for you is they won't give you this initial vector. So usually they'll give you a speed, a scalar speed, which will be, and I'm going to do the scalar like that, v naught. That's a magnitude. And then the angle of elevation, which will be theta. So your v naught vector, people, if you break it out and use the week 1 material that I taught you, magnitude times cos of the angle is your first component, and magnitude being speed, times sine theta is your second component. So you're going to plug that in place of v naught, and your r naught is simply going to be the initial height of the projectile. If it's initially launched from ground, then 0, 0 will be your initial position vector. But usually they'll give you some initial height, okay? So when I rewrite this and put all the components in the right place, I'm going to, combining all the I hat and the j hat terms, because this term here is going to look like t times v naught cos theta t, that's v naught. Eraser's not working too well here. V naught speed sine theta, and then you're going to distribute the t. I hope you can see that your I naught, your I hat, your only I hat term will be speed cos theta times t, that's your I hat, and then you'll have a whole bunch of jazz for your j hat. So I'm going to put that all here. add it all together, you'll have h plus v naught sine theta times t minus 1/2 times gt squared, where g will either equal 32 or 9.8, depending on the problem. So this, folks, is your key right here. If I were you in your lecture notes, even though I put the other one in the box, this is the one that I really focus your eyeballs on. That's what you're going to use for word problems and stuff like that in this class, okay? Now, if I see any of this mg sine theta business from your physics strategies, I don't care if you get the right answer. I want to see this. Okay, so I'm going to do a problem now, and this problem is going to wrap me up for the rest of the class today. So see if you can follow along. Before I find the max height, if it's going to clear a 10-foot fence, how long does it take for the ball to hit the ground, and what is the range? Let me again remind you, I don't care how your physics class did it. I want to see the process and the approach that I'm doing here. So please be open to working it this way, because you're going to work it using this projectile motion, vector valued function. So before I even do any of this part of the problem, I want to see your R of t. Like if I don't see that as step 1, goodbye. That means you don't get the problem, and then you're still trying to, get your little, set of physics strategies and, work the problem, and you don't know what you're doing. So the first thing is, and I'm going to put it in component form. So they're telling me that the baseball is hit 3 feet above ground. That's h. That's that h right here. They're telling me 100 feet per second. This right here is your speed, not your velocity, but it's your speed v naught, and your angle theta is 45 degrees. So before I do any of these problems at all, I'm going to come up with this vector valued function and go for it. So let's just do that. I'll do that right down here. Your R of t is going to look like the I hat component looks like that, 100 times cos of 45 degrees times t, okay? And so, that's going to be what, 100 times square root of 2 over 2 t, and so that's really going to end up being 50 square root of 2 times t. Fine. Now you're going to try to get the j hat components. You're going to have height, that's h, plus the second term here, you're going to go 100 times sine of 45 degrees, whatever that number is, times t, minus, and now the last term in the j hat is minus 1/2 gt squared. So minus 1/2. Okay, what the heck is g? Should I use 32 feet per second squared or 9.8? I'm going to open it up, see if anybody's paying attention.
32.
Former.
32.
Wow.
32.
It's 32. How did you know?
We're not using the real
Because-
like system measurement.
Because they told me
Because we're in feet.
the initial velocity was done in feet per second, and that immediately tells me, aha, they're going to want everything in the English system. So that's how you know you're going to use a 32, and then times t squared. And you can clean this up a little bit. This is going to be 3 plus 100 square root of 2 over 2t minus 16t squared, and then if you clean that term up, let's see, I'll have 50 square root of 2t minus 16t squared. Okay, I want to see this somewhere on your paper, because this is what we're going to use to do the rest of this problem. That is your vector valued function describing the motion of this baseball. So here's the baseball, and goes sailing out there after the baseball player hits it. Fine. So what's the max height? Now you have to be careful here, because on my picture here, the max height is the highest vertical height that the ball reaches. So you have to be careful. When do you get to max height? So remember that your velocity vector is always going to be tangent to the line of motion. So if I were to draw the velocity vector initially, there's the velocity vector, there's the velocity vector, here's a velocity vector at max height, and then the velocity vector starts pointing down, 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 because it's still got to be tangent to this curve, which is a downward facing parabola. Do you notice that at max height here, so if I'm going to draw, like here's like this, at max height right there, that the velocity vector is pointing horizontally. So this is the trick. At max height, the vertical component, not the velocity vector itself. Don't go, oh, velocity vector is 0. No, it is not. It's the ball is still moving. The velocity vector only has a horizontal component. The vertical component of velocity is 0. So this is by the way, part A is a multi-step problem. And if I see you get the answer in 2 shakes, I don't care if the answer is right. Goodbye. You're not using the approach here in Calc 3. So here's what you're going to do. After you do step 1, which is go get me the vector valued function describing the motion of the ball, you're going to go get the velocity vector. I want to see it. So R prime is, and then when you take the derivative of 50 squared root of 2t, its first component is going to be a constant. And then when you take the derivative of the second component, you'll get 50 squared root of 2 minus 32t. This is the vertical component right here. So what we're doing, and this is the next step I want to see, set it to 0. I want to see you set it to 0, like physically write it down on your paper and solve for time t. Like actually do this, because this is what's going on. So this is an easy problem to solve. Oh my goodness. You're going to go, oh, your time is that weird number. Oh dear Lord. Well, get out your calculator and you're going to find that's about 2.21 seconds. Is that the answer to part A? Not only no, but hell no, but I'll give you partial credit if you have this. It means it's what time it is when the ball reaches max height. So after the baseball player hits the ball, if you wait 2.21 seconds, the ball will have obtained max height. So the actual max height is you're going to plug this in to the vertical component of position, which some physics books might go, well, that's Ry or whatever, because that's the vertical. Well, the vertical component of position is simply the second component here. It's this thing right here. So if you substitute 2.21 into the vertical component of position, oops, and then whip out the calculator because you're going to need it. That's going to be some weird number here, 2.21 squared. You'll get approximately, I'm going to round to the nearest foot, 81, and it's 81 feet. That's about how high the ball is going to get. And this is the answer for part A. Okay, now the next thing is letter B. What do they want to know? What do they want to know? They want to know if the ball is going to clear a 10-foot high fence, located 300 feet away from home plate. So 300 feet away from home plate, we have some fence right here. Now, if the fence is too high, the ball is going to smack right into it and hit the ground, right? But if the fence is low enough, and they're telling us it's only 10 feet high, the ball will clear the fence. So we want to know, is it going to clear the fence? So this is a multi-step problem. What they're telling me is at the horizontal component, so we're looking at the range here, at 300 feet away from home plate. So essentially your Rx is 300 feet. And if you look at what your horizontal component is for your position, it's 50 square root of 2t. So look at this and solve for time t, because this is how long it's going to take the ball to make it 300 feet away from home plate. And so the time is this weird number, 300 over 50 square root of 2. And when I use my calculator, I get roughly 4.24 seconds. So at 4.24 seconds, the ball horizontally, the horizontal component is 300 feet away. So now what? Well, now substitute this into the vertical component of position. So the R of Y. So physics people like to use this notation. So what I'm saying is your R of Y evaluated at 4.24 seconds. So here's your vertical component. It's that big old quadratic here. You're going to go, okay, what's 3 plus 50 square root of 2 times this time, which is 4.24 seconds. minus, and I'm running out of room here, got too much junk, minus 16 times time squared, so that's 4.24 getting squared, and that's going to be some nasty number here. And I get the vertical component is roughly, I'll round to the nearest foot, 15 feet. So now let's answer the question. I'm still doing part B. Will the ball clear the 10-foot high fence if at 300 feet away the ball is 15 feet high? Yes or no?
Yes.
Yes, it will. In fact, it's got extra room to clear. It's got 5 extra feet. So it clears the fence very easily and makes it past the fence. Phew! Okay, fine. Now letter C, new problem. How long does it take for the ball to hit the ground? Do not set the velocity vector equal to 0. Well, when it hits the ground, the velocity is 0. No, because the ball is moving when it hits the ground. So you don't want to do that. So how do you figure out when the thing hits the ground? Well, if you look at your position function here, when the ball hits the ground, so way over here, the vertical height at ground level is 0. So the way to start off part C is you're going to set the vertical component of position equal to 0 and then solve for t, and that'll give you how long it takes to get
Is it frozen for anyone else?
It's frozen for me.
Yeah.
Yeah.
All right. Rest in peace.
What a way to end the class.
I mean, hey, the velocity of the ball wasn't 0, but the recording is.
Same goes for my brain cell count.
Dude, no. Okay, hear me out. Oh, I'm fuck. Oh, still recording. I'm vibrating right now. Oh my lord, this.
Dude, David,
Yes.
I don't know. I wish I could do something for you. I felt that pain the first quiz, and boy, I never wanted to feel that ever again.
Dude, it's so embarrassing. Not only did I actually do competently. Oh, never mind.
Sorry, guys. Remember I told you really bad internet? I'm sorry. So, can you still hear me?
Yeah.
Yeah.
Let me know if you can. B squared minus 4AC all over 2A. I got to go quick until my internet doesn't bomb out. Holy crap. So the A is negative 16. Be careful here. Your B is the 50 square root of 2. And your C is the constant term. He's the 3. So when you plug into this quadratic formula with all the right slots and then use your graphing calculator to get you're going to get 2 answers because of the plus or minus, of course. You're going to go, oh my God, negative 50 square root of 2 plus or minus the square root of 50 square root of 2 squared minus 4 times A times C. So that's 4 times, A is negative 16, and then C is 3. And sorry, this is a big honking mess here, all over 2A, but A is negative 16. And then you're going to get 2 answers. Now, the 2 answers that I get are, one of them is negative 0.0013, and this is seconds, okay? We're solving for time. And the other answer is 4.46 seconds. Which one of those answers do you think is the correct one for letter C?
Positive one.
Very good, because we can't go backwards in time, at least when we're playing baseball. So that's the answer for part C, and we're almost done with this problem. Bear with me. What's the range? So when the ball does actually hit the ground, how far away from home plate is it? Well, we know how long it took. It took 4.46 seconds for the ball to hit the ground. So what's the horizontal distance away? Well, going back to your vector valued function up here, I keep referring back to that because I want you to get, that's where we get all this information from. You're going to plug the time that you just got, 4.46 seconds, into the horizontal component of position. And that'll give you how far away from home plate, which is what they're basically asking you, how far away from home plate when it lands. That's what they're asking. So you're going to substitute into, and right now I'm writing on a visible ink because my computer is too hot. Are you guys still there?
Yep.
Okay, sorry. I have one of these cooling stands, but it doesn't do a very good job of cooling my computer. These computers run hot. So you're going to go, okay, well, the horizontal component of position is easy because that's just 50 square root of 2 times time. So what's 50 square root of 2 times 4.46 seconds? Eek. And I get roughly 315.5. And what's my units here? Seconds, miles,
Feet.
inches. Yeah, it's feet. So that's how far away the ball is, boom, when it hits the ground. Okay, fine. So that's how far away from home plate it is when it hits the ground. And yes, you're going to have one of these problems. Don't even ask. On the midterm, like from top to bottom, know how to do all of this. Find the vector valued function, find the max height, do all this stuff, okay? I'm done. If you need to leave, bye, see you later. I'm going to stop the recording. I'll stay for about 5 minutes for any last minute hair on fire questions. I'd be happy to entertain, okay?